Homework 4.3, Properties of Logarithms, Video 2. Homework due Friday, May 29th at 11:59 p.m. The following video is associated with homework questions 4 through 6 and is also incorporated in questions 10 through 19. Just a reminder, that means that 4 through 6 is just like these, whereas 10 through 19 uses this rule in conjunction with other rules. In the first video, we learned the product rule, which is summarized here. The log of a product equals the sum of the logs of the product's factors. But if there's a product rule, then it stands to reason there's a quotient rule. Oh, I wanted to say something also. For those of you who are heading towards calculus, about 3 or 4 weeks into it, you will learn a rule called the product rule and the quotient rule. It will not be these. The better name for these are the product rule for logarithms, the quotient rule for logarithms. In calculus, you will learn a product rule for something called derivatives and a quotient rule for something called derivatives. So just keep that in mind that sometimes the name is recycled depending upon context. So what is the quotient rule? As if these examples couldn't give it away. Well, the product rule is a rule for a logarithm of a product. So the quotient rule is a rule for the logarithm of a quotient, aka the answer to a division problem, which we can write as a fraction. So the quotient rule starts with the log base b, any permissible base that's positive but not equal to 1. Log base b of m over n. And I bet you can figure out how this is going to work. When the argument is a product, you get a sum of logarithms. When the argument is a quotient, you get a difference of logarithms. So log base b on the left and log base b on the right. Left and right of the subtraction sign. And the rule is the numerator goes in the first log, so log base b of m, and the denominator goes in the second log base b of n. And so the quotient rule is the logarithm of a fraction equals the logarithm of the numerator minus the logarithm of the denominator. Same caveat as before, where m, n, and m times n are all positive. For the same reason as before, not m times n, m divided by n, although honestly if the quotient is positive and so is the product and vice versa. And again, that caveat is just because it's possible to have two negative numbers here, which would make both logarithms undefined. Okay, not real. But if I put the two negative numbers on top of each other, they would turn into a positive, and therefore this logarithm would be okay. We will always assume in these problems that everything is positive as necessary. So let's apply the quotient rule to both of these. In fact, I challenge you to pause the video now and see if you can apply the quotient rule to both of these. You really don't have to overthink it, at least when you expand it into the difference of two logarithms. But both of these will have logarithms that you can answer after expanding it into the difference of two logs. So if you haven't done so already and want to, I invite you to pause the video. In the meanwhile, I'm going to do these. Well, here's a log of a fraction. And the quotient rule says a log of a fraction equals the log of the top minus the log of the bottom. These logs are base 7. So log base 7 of the top minus log base 7 of the bottom. One of which we can answer. What is log base 7 of 7? We had a property that says what that equals. I actually even wrote it in the previous video. But as long as you remember that a logarithm is asking a question, sometimes it's easy to answer. The question this one is asking is, what power turns 7 into 7? And the answer is 1. So the first logarithm can be evaluated without a calculator to get 1. The second one we can't because it's just a y. We don't know what that equals. So if this were a homework question, and it was, that's where I got it from. The final answer would be 1 minus log base 7 of y. Second one kind of runs the same course, at least initially. It's a logarithm of a fraction, specifically natural logarithm. And do you remember what the implied base of natural logarithm was? Recall that natural logarithm means log base e. So if we have an e in an argument, we might need to keep that in mind. Oh, look, we do. All right, so log of a quotient is the log of the numerator, so natural log of e to the 5th, minus the log of the denominator, so natural log of 19. The natural log of 19 can be easily evaluated in a calculator, but the directions specifically say evaluate them without a calculator if you can, meaning don't do anything with this. But what about the first one? What's the natural log of e to the 5th? Well, what's the question this logarithm is asking? Remember that its base is an implied e. This logarithm is asking what power turns e into e to the 5th power. Well, a 5th power turns e into e to the 5th power. In other words, the value of the first logarithm is just 5. That's the power that turns the base into the argument. Without using a calculator or calculus and a lot of arithmetic, we're not going to get an answer to 5 minus the natural log of 19, so that's where that problem would stop. So as you can see, the quotient rule on its own really isn't that eventful. It simply says if you have the log of a fraction, you may split it into the log of the numerator minus the log of the denominator, and then if anything else happens after that, so be it. Oh, there is one thing I neglected to mention. Some of you may have already stopped watching. In the previous video, I mentioned that the product rule was the logarithmic version of an exponent rule. The quotient rule is also the logarithmic version of an exponent rule. It's the logarithmic version of the rule that says b to the m power divided by b to the n power equals b to the m minus n power. Because we're not going into details about where these rules are coming from, I'm going to spare you the transition from here to here, but I invite you to search it out on YouTube or something. Since you're on YouTube, if you're watching this, you might be surprised about how much you can follow.